In this video, we are going to study regarding the design of two-way slabs. For design of one-way slabs, you can refer the previous videos. Already we have seen what do you mean by one-way slab and two-way slab. So let me tell you once again what do you mean by two-way slab. So if Ly by Lx ratio, if it is less than 2, then we can call this slab as a two-way slab. Another thing is that the reinforced concrete slab, it is supported on all the four sides. It is supported on all the four sides with their effective span in the longer direction not exceeding 2 times the effective span in the shorter direction. So always what we do, longer direction to the shorter direction, that is Ly by Lx. If it is less than 2, we can call this type of slab as a two-way slab. Another thing is that it has to be supported on all the four sides. Then next, how the behavior of the two-way slab is such that it is going to bend in both the directions. It is two-way slab deformed with significant curvature in two orthogonal directions with movements developed in the principal direction as shown in the figure. Next, I'll show you the figure. In that figure, you can see the bending has happened in both the direction. The next is the bending moments are maximum at the center of the slab and larger moment is developed at the shorter span, along the shorter span. The bending moment in the slab depends upon the following parameters, that is the short and the long span, that is Lx and Ly. Then next is the edge conditions at the supports, whether it is a fixed, free or continuous. Then next is the magnitude and the type of load on the slab, whether we have UDL or concentrated loads. Or the reinforcement which we are going to place, it is along both transverse as well as the longitudinal direction. In both the directions what we do, that is along x direction as well as along y direction, we are going to put the reinforcement. Why? Because in this direction also slab is going to bend, as well as in this direction also slab is going to bend. So that we can see it in this figure. So if you see, this is one two-way slab which is supported on all the four sides. So you can see that it is supported on all the four sides. So the load transfer, it is going to take place on all the four edges. So you can see here load transfer is happening in all the four edges. So you can see here to this it is transferred in the trapezoidal load. This much area of the load will be transferred on this beam, and the triangular portion will be transferred on this beams or supports what we have. So if you see, this is Ly and this is Lx. So if you see, Ly is nothing but the longer span, so the bending happens in this way, that is the My, you can say. And if you compare it with the Mx, that is Lx, so you can see that here larger deflection has bending has taken place. Why? Because along the shorter span what happens that we are going to have more movement compared to the longer span. So therefore main reinforcement will be provided along the shorter span. So along shorter span what happens that main reinforcement will be provided. So in two-way slab what happens is that main reinforcement, it is provided along both the spans. But preferably if you compare this longer shorter span as well as longer span, so shorter span it is going to have more movement compared to the longer span. Then next, if you can see the deflection diagram also, this is how our slab is going to deflect in both the direction, both the orthogonal direction. Then next is here in this we are going to have a simply supported slab. When a slab is supported on all the four sides, is subjected to a transverse load, the bending of slab in the two principal direction causes the corners to curl and lift up as shown in figure due to non-uniform variation of load transmitted to the support. So what happens is that when the load is being applied in this way, so these corners they try to get lifted up. They try to get lifted up. Right? This what get the two principal direction causes the corners to curl and lift up. Simply supported slabs which do not have adequate provision to resist the torsion at the corners. If the supports are not restrained and to prevent the corners from lifting, the maximum moment per unit width are specified in IS 456 2000 code and can be computed by the following equation. So there are two things now, whether it is restrained or not restrained. So for example, if you are going to have simply supported slab which is not going to have adequate provision to prevent the corners from lifting, then what happens is that following equations we can use. That is mx is equal to alpha x into w lx square, my is equal to alpha and y into w into lx square. So if you compare here both the direction, we have lx itself, that is a shorter direction. So if you see the slab now, when the load is being applied, what happens that this try to get all the corners, they try to get lifted up. If there is no proper restraint, so we can use this what you can say formula so as to calculate the movement along x direction and y direction. So this is as per this, already it is being given in the codebook, that also I'll try to show, where mx and my are the design movements in x and y direction. So this mx and my are the movements in x and y direction. W is nothing but the UDL on the slab. W is nothing but the UDL on the slab. LX and LY are the short span and long span dimensions of the simply supported span. So LX and so here we are going to have shorter span itself. Then next is this alpha x and alpha y, what we have, these are nothing but the value of coefficient. So this is not ax, this is alpha x, this is alpha y. Alpha x and alpha y are given in table 27 of IS 456 2000. So if you refer this so you can see now here in the annexure D, they have given slab spanning in two directions. Slab spanning in two directions. So here they have given restrained slab. Restrained slab, when the corners of the slabs are prevented from lifting, the slabs may be designed as specified in D1.1 to D1.11. Right, so when it is being restrained, you can use D1.1 till D1.11. So up to this you can, these criteria you can use. So when the slabs are restrained from lifting, right, if it is not restrained, that is simply supported slab, when the slab simply supported slab do not have adequate provision to resist torsion at corners. When it is restrained, you can use these above clauses. If it is not restrained, you can use the below clauses. Prevent the corners from lifting. The maximum moment per unit width are given by the following equation. So this is what equation just now I had shown you: alpha x into wx lx square, alpha y into wly square, where mx my are nothing but moment, w is nothing but the UDL, lx and ly are the short span and long span. So alpha x and alpha y are the moments given in table 27. So this is the table 27 of IS 456 2000. If you see the sentences, if you see, read the sentence, they have given bending moment coefficient for slabs spanning in two directions at right angles simply supported on four edges. So based on Ly by Lx ratio, so we have to calculate the ratio, whether it is 1.2, 1.3, 1.4. Based on that, we are going to get this coefficient values. That is 0.93, 0.94. This is alpha x value and this is alpha y value. So same table I had shown here, what table just now I had shown. The next is clause D2.1.1 of IS 456 code specifies that 50% of the tension reinforcement provided at mid-span should extend to the support. So therefore what we do, we are going to do the bent up at the support and we are going to take it to the top. So alternate bent up we do, that means one bar will be going at the bottom, one bar will be going to the top. So 50% bent up we are going to provide. The remaining 50% should extend to within zero point 0.1 Lx or zero point 0.1 Ly of the support. Then next is two-way restrained slab. So previously what we had seen, they were not restrained. They were free to get lifted up at the supports. So now if you are going to have two-way restrained slabs with corners held down, so these are the conditions what we have to follow. Restrained slabs are referred to as slabs whose corners are prevented from lifting. So if you are going to restrain it from lifting, so these clauses can be applied. They may be supported on continuous or discontinuous edges. All the four edges of a two-way slab are assumed to be to be supported rigidly against the vertical translation. That means we are going to restrain so that there is no vertical translation. The design moments in the restrained slabs can be evaluated using moment coefficients recommended in IS 456 2000, which is given in table 26 of IS 456. So that also I'll show you now further. These moment coefficients are based on the inelastic analysis or yield line theory with the following assumptions. The reinforcement for positive movement is uniformly distributed over middle strip extending over 75% of the span. The edge strip covers a width of equal to L by 8 or Lx by 8 or Ly by 8 as shown in figure. The next is minimum reinforcement prescribed for a slab should be provided in the edge strip. So these things let me show you. So somewhere here we have, so you can see now this is L by Lx by 8 as well the Lx by 8 as well as this has the Ly by 8, that is the edge strip, and middle strip will be 3/4 of Ly or 3/4 of Lx. Then next is, so what we can do is that they have given coefficient now. So as to calculate now, what you can say when it is restrained, so the for maximum bending moment can be calculated using this equation itself. Alpha x into W Lx square, alpha x into W Ly square, Lx square itself. So alpha x and alpha y are the coefficient which is given in table 26. So this is the table number 26 where they have given the bending moment coefficient for rectangular slab panels supported on four sides with provision for torsion at corners. So here you can see when we are going to have provision for torsion at the corners. Then when it is restrained, we can use this table. When it is not restrained, we can use this table, table number 27. So in this table number 26 itself, they have given different cases. We are going to have 9 different cases. That is different types of panels and moment considered. And here we have Ly by Lx ratio. Based on that, we will try to calculate coefficient alpha x, and we are going to have coefficient L alpha y. So now we are going to have different conditions. One is interior panel. Interior panel. So if you see this figure, if you see this figure, this slab, this is one slab for example which is showing slabs. So one you can see now this is internal, so here also we have slab. On all the four sides we have a slab, so this type of slab we can call it as a interior slab. Then next is for interior panels, what happens is that negative moment at continuous edge. So top one value is what we have to get, that is for negative moment, and bottom will be for positive moment, that is at the mid span. So second panel is one short edge continuous, one short edge continuous. So you can see now this is longer edge, this is longer edge, this is shorter edge, and this is shorter edge, right? So if you see only one shorter edge is discontinuous, this is discontinuous, this is continuous, this is continuous, this is continuous. So this is the second panel what we have. Then next is one long edge discontinuous. So if you see here, this is slab number 3. So this is shorter span, this is longer span, this is longer span. So here you can see this longer span is discontinuous, this span is discontinuous. These two shorter span they are continuous, and one side longer span is continuous. This is third slab which shows one longer edge discontinuous. Then next is two adjacent edges discontinuous. Two adjacent edges. So if you see, this is a fourth panel slab. So this edge is discontinuous and this edge is discontinuous. That means here we don't have any slab, here we don't have any slab. On this side as well as on this side we have this slab. So two adjacent edges discontinuous we have. Then next is two short edges discontinuous. Two short edges discontinuous. So here if you see slab number 5, this is long span, this is long span, this is continuous, this is continuous. But short span, if you see here also this is discontinuous, and left and right both side it is discontinuous. So two short edges discontinuous we have. Then next is two long edges discontinuous, that is 6. So this is long span, this is long span, this is also discontinuous, this is also discontinuous. On this side we have the continuity. Then next is three edges discontinuous. Three edges discontinuous we have. So here you can see slab number 7. So this side it is discontinuous, this also discontinuous, this also discontinuous. Three side we have discontinuous, one side we have continuous slab. In that you can see one long edge continuous. So here this is long edge. So this one long edge continuous. Three short edges are discontinuous. Then next is three edges discontinuous. In that one short edge is continuous. So you can see now slab number 8 we have. So this is long edge discontinuous, long edge discontinuous, short edge discontinuous. So only one short edge what we have, it is continuous as per this clause. Then next is four edges discontinuous. Four edges discontinuous. If you see this panel, so what happens is that this is nothing but slab wherein all the four side it is discontinuous panel we have. Then next is slab number 10. So here if you see, it is restrained. It is restrained from lifting. That means here it is provided with the torsional reinforcement. Whereas we have another slab, that is slab number 10, that is simply supported slab, which is not restrained from lifting up at the corner. This is slab number 10. So that is what we can use this table so as to get the bending moment coefficient for those values. Then next is if you see here, we are going to provide the torsional reinforcement here. So the torsional reinforcement is provided at corners where slab is simply supported on both edges meeting at that corner. So we have to provide the torsional reinforcement. So here you can see we have provided the torsional reinforcement. The next is the reinforcement comprising the 3/4 of the area required for maximum mid-span movement in the slab is provided in each of the four layers in form of mesh extending to a minimum distance of 1/5 of the shorter span. So what we are going to do is that the reinforcement what we are going to provide it as a torsional reinforcement, it will be 3/4 of the area required. 3/4 of the area required at the maximum mid-span moment has to be provided in the form of mesh to a minimum distance of 1/5 of the shorter span. So for example, when we are going to provide this as a mesh, this torsional reinforcement, when we are going to provide this as a mesh, so the area of this steel has to be 3/4 of the what you can say mid-span, maximum mid-span moment. And up to what distance it has to be provided? It has to be provided, that is to a minimum distance of 1/5 of the shorter span. 1/5, that is Lx by 5. Here also Lx by 5. So up to this span we are going to provide the torsional reinforcement. Then next is, as shown in figure, full torsional steel is provided at corner, what you can say A. So let me show you this figure. So if you have one slab, now here you can see, now this is one slab with the corners which have been marked as A, B, C and D. So here if you see, here we have a continuity, and here also we have the continuity, slab continuity, right? So when you consider this joint, what you can say corner A, so here both the edges are discontinuous, both the edges are discontinuous. Then what happens is that, as shown in figure, full torsional steel is provided at corner A where the slab is discontinuous on both the edges meeting at that corner. So when we have both the edges which are discontinuous, then we have to provide full reinforcement. Then next is at corner B where the slab is discontinuous only on one edge. If you see at point B, one side it is discontinuous, one side it is continuous. In that case, so at corner B where the slab is discontinuous only on one edge meeting at that corner, 50% of full torsional steel is provided. 50% of the torsional steel is provided. Then next is at corner C, if you take, here also continuity we have, here also continuity we have. So therefore now at corner C, as the slab is continuous on both the edges meeting at the corner, torsional steel is not required. So here what it means now, here torsional steel is not required. So whenever you have discontinuity on this side as well as this side, 100% reinforcement. So when you have discontinuity here and one side continuity, 50% of the reinforcement we can provide torsional reinforcement. So here on both the sides we have continuity, that means we need not provide any torsional reinforcement at joint C. So you can see now this is the middle strip and this is the edge strip, that is L by 8, Lx by 8. as well as this as Ly by 8 we can have, or Lx by 8 itself. So that is 1 by what you can say 8. This is the middle strip and this is the L strip, and we are going to get the coefficient, that is alpha x we have, alpha y we have. Then next is regarding span to depth ratio. In case of two-way slabs, the magnitude of movements will be smaller than the one-way slabs since the load is distributed in two principal directions. So if you see, if you take in two-way slab, so load will be transferred to all the edges. So therefore what happens is that the magnitude of movements will be smaller than one-way slab. Why? Because load is transferred to all the supports. Since consequently what happens is that the percentage reinforcement being small, the modification factor for the tension steel KT is higher, resulting in higher values of maximum permissible span to depth ratio. So due to this, what happens that consequently we are going to have the percentage reinforcement will be small. So therefore modification factor for tension steel is higher, resulting in higher values of maximum permissible span to depth ratios. The following span to overall depth ratio has been recommended in IS 456 in clause 24.1 for two-way slabs with shorter spans up to 3.5 meters. So for simply supported slab we can have 28, and for continuous slab it is 32. The next is regarding the deflection control. The deflection of two-way slabs is controlled by span to depth ratio as we have done in the one-way slabs and beams. In the two-way slabs, the shorter span and the percentage of steel in that direction have to be considered for computation of modification factors. So what we have to do is that we have to use Lx as well as the percentage of steel in that direction for computing the modification factors.